Okay, so yeah, so where were we? Talking about the zeta function. We established Euler's identity, but only on the real numbers, right? So okay, so right, so we got that that the zeta function, we had this product form of the zeta function, p in primes, and that this is true for s bigger than 1, right? And what we really wanted was it to be true for in the complex plane, in the half complex plane, right? Now this function we already have defined on that domain. What we need is to just show that this thing is a holomorphic function, right? Once we show it's a holomorphic function, then agreement on the half line will give us this equality in the whole half line, right? So all we have to do is show that it's holomorphic, and that actually follows from work that we did before. So you may recall that we had this theorem about infinite products, that if you have a bunch of functions and they're holomorphic, then if for all compact sets contained in gamma, as long as we satisfy some sort of wire stress condition, then the product of 1 plus these guys is going to be holomorphic, right? So so if for any compact set we have bounds m sub n that are that can be dependent on k, such that the functions are bounded by these bounds on the compact set, and the bounds, the sum of the bounds converge, then the infinite product of 1 plus the phi sub n's is holomorphic, right? Converges uniformly. Converges uniformly and to a holomorphic function. Okay, so that's something that we actually used earlier. So in this case, right, we have this guy, right? We have this thing over all primes, and so our phi are going to be just the terms minus 1, right? That is to say, p to the minus s over 1 minus p to the minus s, when n is a prime, and then 0 when you have a composite number. Okay, so right, these are the things that we want to look at, right? Okay, so we just need to find the bounds and show that the bounds are summable. Okay, so that's actually pretty straightforward. So you say, well, look, given any compact k in this half plane, right? We know that the real part for all s and k, the real part is going to be greater than some number, which we'll call sigma bigger than 1. Right. Okay. So, right, because of the compactness. Okay. So then take as our bound 2 times n to the negative sigma. Okay. Then of course for n not prime, our function is 0. Our function is 0, so that's certainly bounded by this. And for n prime, for n equals p of prime, well, this thing is, 1 over 1 minus 1 over p to the s. I'm sorry, this, can you write this way? This is, 1 over 1 minus p to the 1 over p to the s times p to the minus s, right? And this thing is smaller than 2. This thing is smaller than 2 because the prime is bigger than or equal to 2, right? And the real part of s is bigger than 1. Okay, and then this part here is just so we get 2 times the size of this thing. Well, the size of this thing is just p to the negative. I'm sorry, it's bounded above by p to the negative sigma. Okay. So it's Okay. So in any case, these things converge, right? So if you sum these guys over all n, right? Because this is bigger than 1, you have this converges, right? And so the infinite product converges. It converges to a holomorphic function, and that does it for us. Okay, so that fixes up the Euler identity that didn't work last time. Okay. Everybody okay? Any questions? Good. I got the thumbs up from Noah. No, it's okay. Okay, so remark that by the same theorem, the product is only going to be 0 if you have a 0 factor in it, right? And none of these factors are 0, and so you know that that this thing is non-zero on that half plane. Okay, so the zeta function, what is to say that the zeta function doesn't have any zeros on that half plane. Okay, so now that I fixed that, let me sort of sketch out where we were. Okay, so remember where we were. We had defined this this theta function, right? So for t greater than 0, we defined the theta function as the sum over all integers of e to the negative pi n squared t, and then using Poisson summation. We got the functional equation for theta, that theta equals t to the negative half theta at 1 over t. Okay, and then from there we got some bounds on the behavior of theta as t goes to 0 and as t goes to infinity. Right, so 1, we got that as t goes to infinity, the difference between theta and 1 decays exponentially. 2, we got as t goes to 0, the function looks like, the function is bounded by t to the negative 1/2. Okay. And at that point, we said that our goal was to get this crazy looking functional equation that would allow us to extend zeta to the entire plane. Okay. So right, to get the goal was to see that pi to the negative s over 2 times gamma s over 2 times zeta s actually equaled pi to the negative 1 minus negative 1 over minus s over 2 gamma 1 minus s over 2 zeta 1 minus s. That there was this kind of symmetric relation that these guys satisfied. Okay, so in particular, that would give us an expression for zeta, right, as pi to the s minus a half gamma 1 minus s over 2 over gamma s over 2, and then times zeta 1 minus s. Right? And you can see that this is going to allow us to reflect, right, to get zeta defined on the other half of the plane. Okay, so just a sort of cool remark that so recall zeta has no zeros. So zeta has no zeros on the plane past real part equals 1. And if we look then, if we look on, so think of for s, where the real part of s is less than 0, notice that 1, gamma has no zeros. This thing here has no zeros. 2, zeta 1 minus s has no zeros. Right? Because 1 minus s is going to have the, since the zero part is less than 0, 1 minus s has a real part greater than 1, right? So the real part of 1 minus s is going to be bigger than 1, and we know that zeta has no zeros there. And the last thing we notice is that this part, 1 over gamma s over 2, this thing has zeros at the poles of gamma s over 2, right? Namely 0, -2, -4, etc. Okay, so once we get this extension, the point is that the point is this: once we extend zeta to the entire plane, all the zeros. So excluding 0, -2, -4, etc. Right? All zeros of the zeta function must lie in the strip where the real part is between 1, 1, and 0. Right? Right? Because we just saw that for where the real part is less than 0, we have these zeros. Right? We have these zeros. These are called the trivial zeros. Okay. And we saw that to the right of 1, we have no zeros. So all the zeros must lie in this strip, the so-called critical strip. Okay. And leads us to, we can state the Riemann hypothesis, right? That says that, in fact, all the non-trivial zeros of zeta lie on the line where the real part is equal to half. Okay, so okay, so now let's go for the functional equation. Okay, it's not the most exciting thing, but yeah, I'm afraid that was kind of the high point. Okay, from here on in, it's just going to be a lot of calculation. Okay, so get ready for it.
Yes.
Okay, so first, technical lemma, always a bad sign. Okay, so technical lemma. If the real part is bigger than 1, then this expression pi to the negative s over 2 gamma s over 2 zeta s equals some integral. The integral from 0 to infinity of u to the s over 2 minus 1 times theta of u minus 1 over 2 du. Okay, so we're going to express this thing as some integral. Okay. Right. This as we mentioned last time, this theta. Well, let me just start. Okay. So let's just start from here. So we'll take the right hand side, and then we'll see that it equals the left hand side. Okay. So we replace theta minus 1 over 2 with.
Is it s minus 1 over 2 or s minus 2 over 2?
S minus 1 over 2. Sorry. S over 2 minus 1. Thank you.
Okay.
Yeah, so it should be a 2. Sorry. Thank you. Okay. So we can replace this as we did last time with just the sum of the e to the negative pi n squared u as n goes from 1 to infinity, right? Because it's, we throw out the 0th term, and then the negative terms and the positive terms, they're the same. So we take half of them. Okay. So just like we did last time. And then here is the point of the estimates that we made for theta. Okay, so the thing is that, remember, theta minus 1 decays exponentially, right? Theta minus 1 decays exponentially, and we also had control over what happens when we go to 0. Okay, those allow you to use the dominated convergence theorem. It's the lemon theorem that I mentioned before, right? As long as you're trapped within this lemon, then you can change the order. Okay, so that allows us to change the order of integration and summation. So we get, let me do it up here. So dominated convergence theorem allows you to change the order s over 2 minus 1 e to the negative pi n squared u du. Okay, and then after that, it's it's just a change of variable. So now let u be t over pi n squared, and you get that this is equal to summation n equals 1 to infinity. We get pi n squared to the negative s squared plus 1. We get t to the s squared minus 1, right? And we get e to the negative t, and we get dt over pi n squared. So just changing variables. Right. Well, some cancellation occurs, right? That pi n squared cancels off this guy. We end up with summation pi to the negative s over 2, n squared to the negative s over 2, so n to the negative s, and we get this integral t s minus 2, s over t minus 1, e to the negative t dt, but that's from n equals 1 to infinity, right? That thing here, that's just the gamma function, right? That's the gamma function at s over 2. That's a gamma function at s over 2, and so we get, right, pi to the negative s over 2, gamma function s over 2, and then summation of the n to the negative s, that's a zeta function. Okay, so nothing too fantastic. Okay, so that's the technical lemma. It allows us to express this thing as this integral. Okay, so now for I think basically for notational convenience, let's write. Let's express this thing. Pi to the negative s over 2 gamma s over 2 zeta s, zeta s as, we're going to call that xi of s. Okay. Initially defined on the real part, where the real part is greater than 1. So, okay. So, okay, so the most of the work will be done once we show that that xi has an extension to the entire plane. Okay. So okay, so the main thing we have to do now is prove the following: that that xi, which is initially holomorphic in the, where the real part is bigger than 1, has an analytic continuation to the plane as a meromorphic function with simple poles at 0 and 1. Okay. Further, it satisfies xi of s equals xi of 1 minus s. Okay, this this is the functional equation that we said was our goal. Okay, it's just more neatly expressed with xi. Okay. Okay, so yeah, this is also not the most exciting. It's again sort of like a lot of integrals. Okay, so let's start off. So xi is, as we said, I'm sorry, xi of s is I to the negative s over 2, gamma s over 2, zeta of s. But we have this integral expression that we just did the technical lemma for. Right? So it's u to the s over 2 minus 1 times theta of u minus 1 over 2 du. Okay. We're going to call this theta minus 1 over 2 c. Okay. Just to again, this is just for notational convenience. Okay. So okay, so and then we take this integral and we break it into two parts, from 0 to 1 and from 1 to infinity. Okay. So just a side comment. Because we have this relation, that changes into a functional relation for psi. So we get that psi of u equals u to the negative 1/2 psi of 1 over u plus 1 over 2 roots of u minus 1/2. So that's just a calculation. Okay, so let me write this out. We're going to have u to the s over 2 minus 1 times psi of u, but we use the functional equation for psi. So u to the negative 1/2 psi 1 over u plus 1 over 2 roots of u minus 1/2 du. And then we have the other part from 1 to infinity. U s minus 2 minus 1 psi of u du. Okay. Okay. So at this point we do a change of variables. So change of variables. Let v be 1 over u. So du is negative dv over v squared. That gives us the integral from 1 to infinity minus the integral from 1 to infinity of v to the 1 minus s over 2 times v to the 1/2 c of v plus v to the 1/2 over 2 minus 1/2 dv over v squared plus the other thing. Okay, so if you don't mind, I'm going to write everything. I'm going to change all these v's to u's. I should have just. Okay, so and then whoops. Let me write this out. So we'll have two expressions. one of which will be oh, I'm sorry. This was from infinity to 1, and then when you reverse it, you get rid of the minus. You get rid of the minus sign. Now it's 1. Now it's 1 to infinity. Okay, so you get two expressions. One is u to the negative s over 2 minus a half. Right, that's from this and this, and then you have plus u over s u to the s over 2 minus 1, everything times c of u to u. Okay. And then you have the integral from 1 to infinity of these terms. Okay, of these terms divided by u squared. Okay. Those turn into 1 over s minus 1 minus 1 over s. Right. So, but you have the integral of these terms. U to the 1 minus s over 2 times this, everything divided by u squared. Okay. And if you work it out, it's just elementary calculus. You get 1 over s minus 1 and 1 over s. Okay. And that's about it, actually. So that's, once we get to this point, the point is that, again, this thing has exponential decay. And so if you create a difference quotient with this integrand, that difference quotient will converge uniformly because of the exponential decay. And so you can change the order of you can change the order of differentiation and integration. Okay, so that means that this thing is differentiable, so it creates this yields an entire function. Okay, so this is actually an entire function here. Because of the decay. So okay, so what you get is that that xi is this something that has poles at 1 and 0 plus this entire function, and so you get that in fact it is a meromorphic function with simple poles at 0 and 1. And then it's straightforward to see that if you substitute 1 minus s for s everywhere, then you get the same expression. So this expression is actually symmetric between s and 1 minus s. Okay, so that gives you this result. That xi can be extended to so we had this initial expression that was valid for the real part being bigger than 1. And then we see that actually we can express it as this thing which is valid on the entire plane and agrees with that on the real on that half plane. So that gives us the extension to the entire plane. Okay, so everybody okay? Okay. So that finishes it, basically. So as a corollary, we say that zeta has a meromorphic extension, meromorphic continuation to C with one and only one singularity, a simple pole at s equals 1. Okay, and the proof is just to say, well, look, we see that gamma of S, by definition, is by the definition of Xi, zeta is, I'm sorry, zeta of S by the definition of Xi is just this, right? This guy was meromorphic with simple poles at 0 and 1. This 1 over gamma S at S over 2 was entire with simple zeros at 0, -2, -4, etc. Right? And so the simple zero for this cancels off the simple pole there. You're left with a meromorphic function with one pole at 1. So this thing has a simple pole at 1. That's the extension of those.
Don't
Yeah.
we need another gamma and then image to get rid of the poles -2, -4?
No, the 1 over this has zeros there.
Yeah, so those would, like, if this were just the formula, then you get poles at -2 or -4 for zeta and so on. But, like, I think in terms of the functional equation, you should have, like, a gamma of 1 minus S, the whole over.
Oh, I'm sorry, thank you. Yeah. Sorry. Thanks. That is maybe the appropriate way to end the course with with. Right. We need gamma 1 minus S over 2. Right. Thank you. Yes.
That's oh. Wait, what? I was gonna say, oh, that's C, not theta.
Otherwise, you'd have.
Okay,
like,
sorry,
just
sorry, yes.
functional equation, but also otherwise if you have poles, then-
Wait. Hold on.
That's not how we define.
No. That's right as it was. I'm sorry. That's right as it was, right? Because C was, right? C was pi negative S over
Yeah,
2.
this is all good.
Gamma S over 2 times zeta of S. Right? So that was okay. It was. No, you're good. You're good. It's okay for you to make a mistake. Okay, so that's it. Goodbye.
Thank you, Papa.
I know. Thank you all for checking all my mistakes, for catching all my mistakes. Yeah, no, I've enjoyed having you guys as students. Although it was really stressful.